So thanks for inviting me and for organizing track on our favorite topic. I don't think I have ever spoken at a conference where the previous talk, among other things, was a project that has won the Nobel Peace Prize. Nobel Prize in Physics in CERN. So it's like a high bar to follow, but the other talks have been good. I will try to do my best. I'm here to talk about what I have been calling continuous performance engineering, something I have been doing for the past 10 years in various database companies, and now with my own company trying to productize and evangelize it. Doing this presentation, I realized that everybody else is talking about continuous benchmarking. So this is where we are. We haven't even agreed on what we should call this thing that we know we need to be doing. But I will, after this talk, maybe adopt this as well, because I realized that majority is gravitating there. There was a poll earlier, but people have changed a little bit. So this is, of course, Fosdem, and out of Fosdem, this is the few hundred people who actually care about performance. But is there like somebody in the room who, not just you, but like in the project, there isn't really any benchmarks and nobody's doing benchmarking? Yes. This and for some projects this is actually valid. But then maybe the second option, yes, we do benchmarks, but not running continuously every day. But yeah, like once a year with the release candidate, I'm told to test it. 10 or so people, maybe. So I think things are not as bad. We are making progress. So I think the number 3 is probably going to be popular. So we do have benchmarks running every day in continuous integration, but we don't actually look at the results, or even if you try to look at the results, they are not very useful. Who would identify as this one? Seriously? Okay. So number 4, we have benchmarks in continuous integration. We run them every day at least, or maybe every commit in the best case. And we get actionable results. We assign tickets to the engineer who did the regression, and they are fixed within weeks rather than in December before Christmas. No, okay, and most people are just listening, that's fine. So fairly even distribution. This is still better. I did this some years ago, and there was like 1 who is in number 4. But like I said, of course, this is like maybe out of all of Europe, the engineers who care about performance might have been in this room. So not so bad. We are making progress. But still, if you ask the same question, like about unit testing or testing, like who has automated testing that, and not even like flaky tests, we have good results, and then if something fails, we probably catch it in the pull request, don't even merge it to main. This is basically everybody doing this for 10, 15 years at least. I had in 2006 a project where we had Nyrkiö. So one guy actually had a phone, and with his own fingers he had 100 tests that he would physically press on the different buttons and user interface. He was finished at 15, 16 in the afternoon, went home, and in the next morning he took another phone and did the same programming. This of course never happens anymore. But with performance, we are a little bit behind, I would say. It's not like a given that all the projects have some performance tests, and we know which tools to use, and we just put some YAML lines into GitHub, and it just works. So we are, I would say, 10, 20 years behind. So we are like the Velociraptor, which is the fastest dinosaur. So it's fast, but it's not there. And where is Augusta and Kemal? Are they here? Yes. So I had to steal your slide, because actually this is the problem. This is exactly the problem. I think there are some other problems. One is that performance and benchmarking is kind of difficult. Automated deployment, I think, is also difficult until we had tools like Terraform or something which you can just, let take care of the hard problem. But the thing with automated deployment is that when we do software, we do need the deployment. Like otherwise, there is no point in what we are doing. We can kind of postpone the performance stuff until customers really complain. So this might be one reason that you really had to solve the deployment. And also, to do benchmarking, you also need the deployment. So there is a dependency. You need to solve the deployment problem first anyway. Now when I have had 2 years a startup where I'm trying to sell performance and benchmarking related services to companies, one thing I find that the performance engineers are often very busy. It might take like weeks or months to talk with them because they are at some important customer fixing performance issues in production. And because we are fixing performance issues in productions, we don't have the capacity to do to kind of evolve the tooling that we could fix them before they get into production. The other thing is, and I used to do this as well, sometimes it's kind of nice to be the hero, that you get to work with the most important customers, and you go there and spend some days doing something, and then it's fixed, and everybody's really grateful. The account manager takes you to a nice restaurant, and then you fly to the next place and do the same thing again. So maybe we don't want to fix it, I don't know. Certainly, and this was like genuinely my slide before I saw the Datadog talk, but part of the problem is that math is kind of difficult, but unfortunately we are going to need it. So that is probably one problem as well. And later when we talk about the tuning, which also has been covered a little bit here in previous talks, I find it for most performance engineers actually unintuitive how to tune a server to get repeatable results. So what I'm trying to say is that maybe we need to do what was done for QA testing and deployment. Some years they had like a DevOps movement. First time I heard about DevOps was in Fosdem, probably like 15 years ago or so. And if there was to be like a continuous benchmarking movement, these are some people and conferences and open source projects and companies that you might want to follow. Scott Moore is very active on YouTube and LinkedIn, so he's a good place to start. And if it wasn't obvious, Nyrkiö is the company that I have been pushing for 2 years and try to. The goal is to mainstream some open source tools that in the past 10 years have become developed and open sourced and so on. So I'm here to tell you what I've learned and made available in the past 10 years, and I hope that you will also tell others about these solutions. That continuous benchmarking actually is possible and achievable, and getting the repeatable, stable results is something we can do if we share the knowledge how to do it. And from here on, the talk has 3 points. If you have ever seen Finnish President Stubb, there is not one interview where the answer wouldn't be structured into 3 points. So I believe this is a good way to go. Now for the first one, we had kind of synchronized before. that the benchmark design in itself is already hard, even like let alone doing it like repeatably or continuously. So I'm not gonna repeat a lot what was already in the previous talk. And part of this is kind of well established already. So the nice thing is we have these frameworks. Typically, each language has like one or two. So if you are writing in Java, you do JMH and so on. So that's kind of well understood. And then, of course, if you use these frameworks, you can relatively easily put them into a GitHub workflow or Jenkins and so on. So here we have a good starting point. I have also, in my career, developed frameworks to run like distributed benchmarks. So like deploy an entire MongoDB cluster and then deploy some application that creates some workload and then run the benchmark. And then, of course, because it's in the cloud, all these servers are going to disappear, so you need to collect all the log files and results and so on. And it's quite complicated to do that. I believe this is an area where solutions are not very established yet, but I see a lot of opportunity for innovation here. So I'm not going to talk more about that, but it's like to highlight an area where I think this isn't very established yet. But even if you start with single node benchmarks with the well-established tools, that's a good starting point. I want to mention one open source project that is like relatively popular and active, and I have also like forked a Nyrkiö version of this one, but this has existed for I think 6 years at least, and has several contributors. And so what this project does is you run your benchmark with the frameworks from the previous slide, and this GitHub action benchmark has parsers that understand the output of all of them, and you can of course contribute more. I saw recently some activity. I've contributed also a parser for if you want to just use like the time command line utility to like execute something from the command line, which of course isn't very like a high fidelity result, but it can be like a simple way to do at least something. So hopefully that will get merged upstream. And what this then does is it collects your results, and they have some interesting way to basically maintain a database or like a JSON file in your GitHub repository, which I wouldn't do because your analytics gets kind of embedded in the test history itself. But it's kind of a simple way. It doesn't cost anything when it's in your Git repository. And then it has threshold-based alerts. And the default threshold, and this highlights the problem I'm talking about in this talk, the default threshold in this tool is 100%. So if your performance degrades 2x, then it will create a ticket or depending on configuration, failure, pull request, and block it. But 2x is quite large, is the point. So we would want to maybe catch regressions much smaller than that. Right? Okay. And this leads to topic number 2. How do we do change point detection? What is change point detection? So topic number 1, we have designed benchmarks. We try to design them well so that we get like useful results, but they are still noisy. This is from an old publication we did at MongoDB. Excuse me, I think I need to take medicine. I forgot to take it before the talk. So these were some MongoDB tests. I think at least the first one is one of the worst case scenarios that we had in 2015. And in this picture, there is one regression on one of the graphs, but everything else is noise. So how do you work with this? Even like looking at it as a human, it's not easy to spot where is the regression, let alone having something automated where you have no human looking at it and it should find the regression. But this is normal. I don't know, those of you had, like in the Datadog case, for example, 20-30% up and down. And this is not, I noticed you, for example, had variance in your slide. We decided in MongoDB to look at the range from minimum to maximum result, which is stricter, but we felt it was kind of like meaningful that we want to have all test runs behaving well. And so then you get up to 70% outliers sometimes. But there is an actual change that is persistent. So this was caused by something in the actual Git commit at that point, right? So this means when I was on the team, there were 4 of us. So in a month, each of us had 1 week where we were tasked to triage results coming out of the CI system, and you can imagine that mostly they were false alarms when input data is like this. This is something more recent. This is from the Nyrkiö site, and some of our users choose to publish their results, especially for open source projects. It's convenient because then contributors don't need to create an account. And here also, this is Turso database, a Finnish-American project, very popular. They get like 20 pull requests per day, many of them from external contributors. And two simple tests: select one, select count star. This is with the GitHub default runner. Once in a while you get these kind of hiccups up and down, 40 to 50% compared to the... Here you can, of course, with the human eye, you can see where is the kind of normal result. That's the one that is kind of without these effects from the infrastructure. So now if we do threshold-based alerting on this kind of data in MongoDB or Torso database, it's a first idea that comes to mind. Here is a generated data set, and on these 2 graphs, the green line is like an actual change, which could be like a regression, and everything else is false alarms. And in 2015, this was my job. So 1 week every month, I would come to work on Monday, and I would have to look through. There were like issues created out of all of those, and you know already before you look at them that maybe today 100% of them will be false positives, or like once a week there would be like an actual regression that you then could file and send to the developer to fix. And we were lucky, so the first thing we tried, something else than threshold-based alerting, was this kind of algorithm from Matheson and James that had just been published a year before. And you need to understand some math, but we were also lucky that we had an intern that actually studied math and went back to do a master's and PhD later, who then did the first version of what is today the Ottawa incubating project in Apache. And this is so this is the same graph. So this is the same time series now in both of these graphs. The top one is the change detection algorithm, and the bottom one is this, like just comparing like some percentage compared to the previous point gets an alert. So the key and the key of of how do you get this kind of better performance is that it looks at more data, of course, than just the previous point or some small window. And the key word here is many monitoring tools that have these kind of functions have been designed for monitoring production. And that is a different problem than finding regressions in pull request before you commit. Why? So in production, so the two phenomena you have are outliers, which can be like a spike of a single event, and then change points, which means there is a persistent change, like in the middle here in this demo data set. And we are now only interested in change point detection. So we want to, if there is a regression in the actual code, it means like when we rerun the benchmark tomorrow, the regression will still be there. And then everything else that's from like network flakiness or noisy neighbors or so on, we want to ignore. But a lot of the existing tooling actually is designed to also alert you on outliers, and we consider, for us, that's a distraction. Okay, so that is change point detection. You can check it out on Ottawa Apache org. But this was transformative for me and the team, and it since we published, it has been used by many other companies, and that was the first time that we started believing that this continuous benchmarking is possible, in the sense not just that we can execute the benchmarks, but also that we can automatically analyze the results in an actionable way. Also, actually, back then we did another project where we looked at the other problem, is that why is there so much noise in the benchmark results in the first place? And now I can a little bit, there's a little bit overlap between the previous talks, but let's say if you were here for the data talk, this is like wrong answers only slide, so don't like, you already know the answer. But if I ask some people who weren't sitting in this room today, then the typical answers are, well, you shouldn't use cloud infrastructure for benchmarking, probably we had noisy neighbors, or there is some other kind of bad cloud instances. Actually, this previous talk from Gabor, and it's true that sometimes you observe this correctly, and there is a reason why this kind of change in performance happens, but it's not across the population. It's not well understood what are the reasons why we can't get like easy to analyze, reliable performance results. And again, we had to go back to our core principles. That let's apply scientific methods, so not just math, but also like, hey, let's stop, quoting things that you read on somebody's blog, and let's get to work, do some experiment, and see what the results are, and then you repeat this. We actually spent 2 engineers spent 3 months where the objective was to find out that what would be a good configuration in Amazon, in our case, to minimize this range from minimum and maximum result of benchmarks where we knew that there was no regression. In fact, we benchmark like the same commit all the time, 25 times. And here is a fun exercise you can do. I'm not going to read all of them, but we will come back. So we kind of retroactively listed the assumptions, because this is how science works. You have a hypothesis, then you test, and then you test either confirms or invalidates the assumption, and then you go to the next one. And these were assumptions that were built in to our benchmarking infrastructure, but they had never been validated. They were just accepted as fact. So, for example, at the end, if you read the third one, there was this kind of belief that when you launch cloud instances, you can kind of sometimes get bad instances for some reason, like maybe noisy neighbor, or maybe they're just bad without neighbors. And because of this, we had a system where we run some kind of test benchmark first, and if the result wasn't above some threshold, we would shut down everything and try again 3 times. And then the third time, we just kind of gave up and ran the benchmark anyway. And yeah, so now what we did was, instead we took like 3 months that we didn't really test MongoDB that much, and instead we tested like our own infrastructure, that can we get better results out of it. So we stopped on a specific Git commit that we knew were good, and so it was always the same binary. And because you don't want to have too many moving parts, right? So you only want to change one thing in the test and keep everything else constant. And then we launched 5 different servers and repeated each test 5 times. And here is like from an old publication again. I copied what I did, and this is what it looks like. So now, immediately when you see this result, what can we see from it that validates or invalidates the assumption on previous slide? This does not show, so like the five first dots on each line is like from the same server, and then like 5 to 10 is the next server. And this does not show that suddenly there would be a server where the 5 dots are significantly different. You see maybe like the first test, there is a bit like a cold cache effect, and then like tests 1 to 5 are faster, but generally there is a lot of variability here, but the variability does not correlate with like 0.5, 10, 15, where we changed server. So this was false. And imagine, this was also at the time when we paid for Amazon instances per hour. So imagine we would start a 16-node sharded cluster in the worst case. They would run this test and say, oh no, this is like, some of the nodes are bad, let's shut down everything. We are already paid for an hour. Let's start 16 new ones. This was all based on a false assumption, but this does happen. The reason this didn't happen for us is we used C3 family instances, which are kind of like a bit more expensive and better quality. If you use the M instances, it's true that you can get different CPU generations. Even if you are using like the same instance type from Amazon, they might, I think they kind of give you like more better CPU than you are paying for or something. But in the C, with the C family, still today, this does not happen. So this is also a good lesson now when you go home. You could do the same mistakes, and I listened to Henrik at Fosdem, and he said that this does not happen. But actually it can happen if you don't have the exact same infrastructure that I had. So you need to do the testing and kind of rigorous scientific attitude. So this was covered. So once we iterated over this and kind of changed various configurations, we found that, for example, the CPUs are not designed. So infrastructure that we use isn't even trying to produce repeatable results. In fact, the CPUs have a lot of features that explicitly change performance all the time for environmental reasons, for example, to save energy. So there is nowadays it's called CPU power, client command line utility, which you can then use to turn off most of these features. so that your CPUs have, and you can use this in the cloud. Some things you can not do on virtualized infrastructure, but actually it turns out that mostly it's not the problem to do benchmarking in the cloud. Like all of these things, if you had your own server in your own laboratory, this would still be a problem, and you would have to turn this off by configuration. The other big source, so we had assumed that if you, like SSDs, of course, are fast, so that has to be good for benchmarking. We had assumed that if you use the so-called local SSDs in Amazon, that's probably good, but that was the biggest source of variation. And the explanation is, if you read Amazon documentation, nowhere does it say that these are local to the server instance. So they go somewhere top of rack or somewhere where, and this is where you have the noisy neighbor problem. So actually the CPU virtualization, CPU virtualization is quite good quality, and you, in my experience, CPU doesn't have a lot of noisy neighbor issues. This is the reason we have. And this could, like, even on the same instance during the same hour, this could suddenly change a lot because of the SSD. And if you use EBS, at the time we used like provision IOPS. This is very stable performance because Amazons are cheap. So if you pay for like 5,000 IOPS, you would get exactly that, not more. And this is what it looked like when we then deployed the improvements in production. So we were able to get more stable lines. In fact, in the MongoDB case, and there is a blog post still public, and there's a link at the end of this presentation. We got all the tests within a 5% range, which is a significant improvement compared to something like 40%. One thing we did as part of this project, we also did tests where we omitted MongoDB completely and just like tested CPU and disk and network performance. And then we thought, hey, why don't we put these in the CI as well? So every day we kind of verified that is the infrastructure still behaving the same as before? And generally the answer is yes. But one day we came to work, what is this, like January 4 in 2018. What happened? All cloud vendors released firmware fixes for Heartbleed, or what was the other one? I think this is Heartbleed. So this is a security fix, and all our performance tests were red, and we thought, okay, so who screwed up? But because we had the canaries running, we say, oh no, actually this is now a problem in the infrastructure. So, but by that time we had already been going a year or so. So this was like a exceptional event that the regression was explained by the cloud environment. Okay, so I've been working on this now last half year again. 10 years later, what has changed? If on Nyrkiö.com, I've done this same kind of tuning, so you can have a GitHub runner, and there are many companies that offer these third-party runners, and often they are like faster than the default runner or cheaper, or often both. And Nyrkiö is the only one who is offering runners that are not faster and not cheaper, but they are better quality because they are configured for repeatable results. Okay, I'm apparently out of time, but using this is quite simple. You install the app, and it's like one line where you can change the runner. And I just want to say I was personally not expecting this, but in some of the tests, this is the same that was in the beginning of the presentation, select count star. when you switch to this configuration in the Turso project, you actually get like for a time period when there is no regression in the code itself, it stays within 1 nanosecond, and I was quite impressed by this. So you can use cloud for continuous benchmarking, and if you have your own hardware, you will have the same problems, and this same configuration is needed. So I think this is a good slide to end. Do we take any questions? Nope. I will hang around here for the rest of the day, so happy to talk.
Sorry, small announcement. Could you please help us and leave through that door?